All right, we are going to look at the standard 1.5 worksheet. We're going to look at the answers for it. One thing right off the bat is take a look at all of your position time graphs. Make sure you are paying close attention to the interval spacing here. Your graphs might look a little different if you were just saying, or if you were just thinking all of these counted as ones. So like this first one, for example, each interval counts as 5 because we're going up to 30. So just pay attention to that. We were given the velocity time graph on number 1, so we want to look at the given velocity of 2 meters per second for the first 5 seconds, and then 4 meters per second for the second 5 seconds. If we draw our position time graph, remember we get change in position or displacement from the area under the curve on the velocity time graph. So if it's going 2 meters per second for 5 seconds, that makes this little rectangle right here with an area of 2 by 5 or 10. So that's how we know this thing goes 10 meters in the first 5 seconds. Again, remember the scale. We're counting by 5s here. In the second 5 seconds, this is 4 meters per second for 5 seconds. So this has an area then of 20 meters. So then our object just goes another 20 meters. So if it started at 0, and yours doesn't have to start at 0 because it's a velocity time graph, so we don't know the starting position, yours just needs to go 10 meters to the right. So it needs to go on our graph up 10 meters and then up another 20 meters. For the second 5 seconds. So this shape is what's important. If yours is shifted down or shifted up, that's okay. Our written description for this one, notice how we are not including the starting position in our written description because we don't know it. We are just given the velocity of the object. We do not know its starting location, so that's not included in the description. We just say it moves to the right at a constant velocity of 2 meters per second for 5 seconds, and then it moves to the right with a constant velocity of 4 meters per second for the last 5 seconds. In the second problem, we are given a position time graph, so we can tell the starting location this time. And our scale is also 1, so it makes it easy. We can just count boxes on our graph. So if we look here, this object in the first 2 seconds, it goes 2 meters to the right, and it takes 2 seconds to do that. So its slope, its velocity here is just 1 meter per second, positive 1 meter per second. So that's where it's drawn on the velocity time graph. Then the next 2 seconds from 2 to 4, it goes 3 meters in the negative direction in 2 seconds. So if we divide them, 3 divided by 2 gets us 1.5 for our velocity. So our velocity is 1.5 meters per second to the left, which is negative on our velocity time graph. Then for the last 6 seconds here, just the slope is 0. So that means it's standing still. The velocity is 0. So we just put a line right at 0. And then our written description, this time, again, we can tell the starting location. So the object starts 2 meters to the right of the origin. Then it moves right with a constant velocity of 1 meter per second for 2 seconds. Then it moves left with a constant velocity of 1.5 meters per second for 2 seconds, and finally it stands still for 6 seconds. In number 3, we are given our velocity time graph, so once again, we do not know the starting location, so we just started at 0. That's an easy number to start at. For the first 4 seconds, it is not moving. Its velocity is 0, so we draw a horizontal line for the first 4 seconds. Then it moves right at 3 meters per second for 3 seconds, so it goes 9 meters in the positive direction. So if you look here, we start at 0, and we're counting by 2s on our scale. So this is 9 on our graph. And then in the last 3 seconds here, it's going negative 2 meters per second for 3 seconds. So that's negative 6 meters. It travels 6 meters in the negative direction. So if it was at 9, it just ends down here at positive 3. Our written description for this one, again, notice we do not know the starting location because it's just a velocity time graph. So the object stands still for 4 seconds. Then it moves right with a constant velocity of 3 meters per second for 3 seconds. Then it moves left with a constant velocity of 2 meters per second for 3 seconds. In number 4, we are given this position time graph. Notice our scale here is counting by 2s. So for the first portion, our object goes from 0 to 6 in 2 seconds. So that means its velocity is 3 meters per second to the right. So we draw a line at positive 3 for the first 2 seconds. Then this object goes 2 meters, remember our scale, 2 meters in 2 seconds. So its slope is 1, making its velocity positive 1 for this section for the next 2 seconds. And then it just stands still for the rest of the time. Slope of 0, so velocity is 0 for the last 6 seconds. Our description, again, we know our starting location, so we can include that. The object starts at the origin. It moves right at a constant velocity of 3 meters per second for 2 seconds. Then it moves to the right with a constant velocity of 1 meter per second for 2 seconds, and then it just stands still for the rest of the time, the last 6 seconds. Here in number 5, we start seeing multiple objects. So object A starts 10 meters to the right of 0, and it moves left at 2 meters per second. B starts at position 0, and it moves to the right at 3 meters per second. Position 0 is just like the same thing as the origin, just another way to phrase it. So we will draw object A first. It starts 10 meters to the right of position 0. So right here we have object A, and it travels left at negative 2 meters per second. So take a look at its starting location there, and then negative 2 meters per second, you can just see the line is going down. One part we know for sure here is that it crosses our axis here, so it gets to position 0 5 seconds later. Because if it starts at 10 and it ends 5 seconds later, that's when it goes at 2 meters per second. Sorry. So if it starts at 10 and goes 2 meters every second, 5 seconds later, it gets to 0. Object B, it starts at position 0, so there we go, right at the origin, and it moves to the right at 3 meters per second. Since our scale here is going up by 6, I think I said 5 for the first problem, but I'm sure we figured it out by now. So if we go up by 6s here, up to 30, 10 seconds later, we get to 30. If we look at our velocity time graphs, here is our velocity time graph for object B. It just is at 3 meters per second. Object A, it is at left at 2 meters per second, so that's why we put it negative 2 meters per second. In number 6, this time we are given the velocity time graph for both of these objects. So as we put in the note here, initial position, the y-intercept can be anywhere. Again, 0 is a good starting spot. Object B, it is going 2 meters per second to the right. Object A, it is going 3 meters per second to the right. So if we look at our position time graph, or to draw our position time graph, we just draw one that should end at 20 for object B, and it should end at 30 for object A, again, assuming we start at 0. Written description for this one, object A travels to the right at a constant velocity of 3 meters per second. B travels right, constant velocity of 2 meters per second. In the last one, we are given the description for this. An object starts to the right of position 0 and moves left at 1 meter per second, and then it moves right at 5 meters per second. So we just need any position to the right of 0. We chose here positive 6. So it moves left at 1 meter per second, so draw a line with a slope of negative 1 for the first 5 seconds, again remembering our scale. Then it travels right at positive 5 meters per second for 5 seconds, so then just draw a line with a slope of positive 5, again remembering our scale, so it should end 25 meters above where it started. Our velocity time graph for this one, left at 1 meter per second is just negative 1 here for 5 seconds, and then moving right at 5 meters per second is positive 5 for the last 5 seconds.